Lecture 7, Forced Harmonic Motion. This will be the first of two lectures on the chapter Forced Harmonic Motion, in which we will conduct an initial investigation into the concept. So a quick recap. This is what we started the course with. This kind of differential equation that we see pops up in a bunch of different places. Or rather, we wrote it a little bit different like this, where omega is interpreted as the angular frequency of the motion, or you can also write it like this. Okay, so this was the starting point. This was chapter 2's work. Then in chapter 3, we introduced the possibility of damping, which amounted to adding an extra term to that same differential equation. And now what we're going to do in this chapter is to add one more term to allow for the possibility of an external force that is being applied in a harmonic fashion. Right, so let's get to it. Let's define what it is that we are interested in. And what we're interested in is this. So the same setup as before, still a spring force, still a damping force, only now we're going to include the possibility of a harmonic force of this form. So something that is applying a force from outside alternately towards the right and then towards the left in that cosine fashion, in a way described by that cosine term. And now the consequence of this, if you want to see how that changes the differential equation that we would normally derive using Newton 2, well, we just go through the exact same process, the sum of the forces, the net force equal to the mass times acceleration. So the same old story. We're not going to go through it again. You can just go and check that you could do it if you have to. But we've done it so many times by now. Let's just state the result, and it's this differential equation. So here, and this term just gets added. So when this was 0, that was chapter 3 then, and that we completely solved. Now we just have this one additional term. And just like in the previous chapters, the differential equation will not be restricted only to systems with physical springs and physical dashpots. You could, of course, get this differential equation in interesting cases with actual springs and dashpots, like a car driving over a washboard road, for example. But it's going to be more general. I mean, it will again be something that is applicable to circuits, for example. Like if a circuit and the loop in a circuit is rotating at some constant rotational speed in a uniform magnetic field, then due to Faraday's induction law, you can get this periodic harmonic force in the circuit. Well, a force in that case would be an EMF in the circuit. So again, the fruits of our labor in solving this differential equation will not restrict ourselves to systems with actual physical springs and dashboards. But we've seen this in previous chapters. Okay, so now we look at this. This wouldn't be our main object of interest. How do we go about solving this differential equation? And our approach to solving it will be the same as chapter 3. Let's see what we have available from differential equations. And what we have available is this powerful result. Again, something that relies heavily on the fact that it is a linear differential equation. And in fact, this proof is actually trivial. Very easy. Any of you should be able to prove it if you think a little bit about it. Look at what it says. It says that if you have a linear differential equation, remember our case, we just have up till n equal 2. So this is stated far more general than we need. We've got the second order non-homogeneous linear differential equation and non-homogeneous because this fx term is non-zero. If this is what we have, then if we can find a general solution in the case where that term is 0, so if this associated homogeneous version of the original differential equation, if we can find a general solution for it and call it yc, and then if we can find just one, exactly one, doesn't matter which one, just one solution of the original differential equation, then the sum of that yc and this yp will be the general solution of the original differential equation. And that's great news, because yc, at least for us, is something that we completely figured out how to find in chapter 3. So all that remains for us is to find one particular solution of that differential equation. So we only have to find one solution of this differential equation. So if Xe is the general solution of the associated homogeneous version of 1, so where this term is 0, if Xe is the general solution of this thing, and this we know perfectly well how to find based on the previous chapter's work, then the general solution of 1 is given by the sum of the two. Now we will refer to that Xe as the complementary solution of 1. And we of course know how to find it. We've completely addressed that in chapter 3. All that's left is to find one measly single solution of this differential equation. That's all. If we can find just one, then we are done. So to find a solution, let's try and make an intelligent guess. So we're playing here. We're going to see if something works. So I want some value of some function x, which if I substitute it in the left-hand side, it's possible for me to get this term. So this is perhaps not an unreasonable choice. So let's see what happens. So I'm going to substitute this into the left-hand side and see if it's possible to get it to turn into this. So I just substitute it and nothing funny going on there. I can group the cosine terms and now I notice something. I see the cosine sign here and the sine term here, and now this is something that I think it's at least the third time that we're going to be concocting a plan using the cosine addition formula. I notice these two terms specifically, and I think to myself, if I can write them in that form, then what am I going to get? And this is the forms you've got to remember. It's worth just flat out memorizing these forms because they often, and we see, as I said, it's at least the third time that we can significantly simplify an expression and find a way forward by using that cosine addition formula. This then simply reduces to that, and the theta terms cancel, and I'm left with what I want. So now I've got an angle of attack. If this is equal to f0 cos theta, and that term is equal to f0 sine theta, then I can have a solution. So let's see if we can realize that. So that x that we guessed will be a solution if these two relations hold. Okay, so I can, well, yes, let's first cover the easy case. Because notice that this omega, which is the natural frequency of the associated homogeneous differential equation, so this is just k over m, if that is the same as the angular frequency of the external force, then look at this term. I can write that as m times k over equal to omega squared minus omega f squared. So this term will be 0 if these two frequencies coincide. The external force's angular frequency is the same as omega, the frequency of the associated simple harmonic motion. So in that case, I've got a term here that is 0. And see, and remember what's going on. I just want values for a and theta that satisfy these two equations. Then this is a solution. And in this case, if this term is 0, then it's easy. Then I just pick theta equal to pi over 2 and a equal to f0 over b omega f. Then I'm done. So in this simple case, it's easy. But let's suppose that omega is not equal to omega f. Then I can divide 3 by 2, which is not the first time that we're using this kind of technique, and I can identify what tan of that theta angle must be. And if I can find a theta from this, then I can substitute it and find for a. Okay, so that is a lot of progress. Perhaps this is how I can find for a and for theta. Now I can also think of this tan of theta. I can also interpret this as a y and an x value and use that to write a in this form. Use that idea to write the sine of theta as b omega f over this, which then simplifies to this. So I can find actual physical expression for a, and where I get theta simply as tan inverse of this expression or that expression. However, there's a small snag here that just has to be kept in mind. The way we've defined it here, and this is a subtle thing that comes into play when you play with trigonometric functions. Sine and cosine have 2 pi periods and tan of theta only have pi period. As if we want to use this nice expression for A, then we just have to bear in mind that this will necessarily be positive. This F0 value will always be given as positive, like 13,000 newtons or whatever, the maximum value of the force of the external harmonic force, or the amplitude of that external force. So this will always be a positive value. So this expression will always be positive if we choose to use it. However, due to this term down here, this term could be negative. And if it is negative, well, this term will be positive, then I'm taking tan inverse of a negative value. That will give me a value between minus pi over 2 and 0, because that is where tan is negative in the at least the portion of tan for which the tan inverse function is defined. So the theta I'm going to get if this value is negative will be between minus pi over 2 and 0. And if I feed that to sine of theta, then I get a negative value. And then that would mean that that would contradict A being positive in this formula. So in other words, if this term is negative, which happens if omega is less than omega f, then theta calculated from this just with tan inverse will get a negative value, which means A would have to be negative for this equation to be satisfied, which will be then in contradiction with this expression if we choose to use this expression for A. So all we've got to remember here is if we're using this expression for A, then we should just remember to take a plus pi over 2 when we calculate the tan inverse. No, not pi over 2. This is an error. I'll fix this in the notes. This should be pi, just pi. Take theta, it will be tan inverse of that value plus pi. So if this value that we get, if you calculate tan inverse to find the angle and you get a negative value, then you just have to add pi, sorry, not pi over 2, pi to it. Or you can forget about this expression and just find theta straight from here and say that theta is equal to tan inverse of this plus multiples of pi, and then do the same old story where you try the smallest one of them in this formula to find A, and then if A works out as negative, then you choose the next theta value like we used to. So either way is fine. This was perhaps the simplest. Just immediately use this expression to find A. You should have all of these constants and calculate the angle, and then just remember to add pi to the angle if it works out to be a negative angle with tan inverse. Okay, it's just a small little thing to keep in mind. So the solution of that original differential equation can therefore be written as the sum of the complementary solution and this particular solution which we've now determined, where xp is in other words of this form. Okay, so this is great news. We've essentially now completely solved even this differential equation, completely. So this is very good progress. So I can just use this expression and then I have a particular solution. And I know how to find xc, that is chapter 3, and then I've completely solved this differential equation. Now, these terms have names. This technically is referred to the complementary solution, but in this case, where x is called the final solution, xp is called the steady state solution, and this xc is called the transient solution. Transient because it goes away. Remember for chapter 3, all three cases we looked at were functions that eventually go to 0. So this one never sticks around. Eventually, it might take a long time, especially if the damping is great, it might take a very long time. But this one will eventually go to 0 and have no more influence. And all that will be left effectively is this one, which is why xp is referred to as the steady state and x of c as the transient solution. But we'll illustrate this with an example. Okay, so exercise 1. Consider a horizontal mass spring dashboard system on a frictionless surface where we're given the mass values and the spring constant and the damping constant, and we're told that x of t is the displacement of the mass from equilibrium, and we're told that's minus 5 meters from equilibrium position at t equal to 0 initially, and it's initially at rest there. and it experiences a harmonic external force at a certain angular frequency, and we've got to find x. Okay, great. So let's start. Of course, we know it doesn't have to be necessarily, as we've seen by now, it doesn't necessarily have to be physically a mass spring and a dashboard. There's some system with a spring-like force and a damping force on it, and now with an external force acting on it. Right, but we'll imagine that it's a mass spring dashboard system. Okay, but as we've seen, it really boils down to what kind of differential equation we're working with. Okay, so now we weren't asked to prove anything from first principles. So let's just start right with the differential equation. As we've seen, it will be in this case. So if you want to set up the diagram, if you had to, and then it would be exactly the same diagram as in the beginning of this lecture. So let's just start with the actual differential equation. So there it is. That's kx equal to, and here we've got a periodic force, a harmonic force acting in on it. First 12,500 Newton in one way, and then in the other way, and in one way, and in the other way at 8 radians per second. Good. All right, so let's name all of these symbols. So mass is, what is it, 25 kilograms, and spring constant, and is 2,500 newtons per meter. Damping constant is 200 newtons per meter per second, so newton seconds per meter. Okay, and the amplitude of the external force is 12,500 newtons. Good, and it's being applied at the frequency of 8.0 radians per second. Okay, and we're also given some initial conditions. Is that initially it's at minus 5.0 meters, and it is initially at rest. Good. Okay, so now we can start. All right, so let's call this whole thing 1. Okay, now we've seen how we've got to solve this. This is a linear differential equation, but it's non-homogeneous. So as long as I can find the general solution of the associated homogeneous one, so when that is equal to 0, then the full solution will be that solution plus any solution of the whole thing. So let's start with the associated homogeneous differential equation. Okay, so we call that the complementary solution that we're going to find, in which in this context is also known as transient solution, because it will die out, as we've already seen. Okay, so this is complementary solution, and this is for the case where it's homogeneous. So let's find this general solution, and this is old story. This is previous lectures work. Okay, so we write it like this, but we also write it in this form. Okay, not that this is really necessary. Okay, well, okay, same thing. Okay, so what is its solution? So as we've seen, we've got to check if it's critically damped, under or over damped. So we calculate b squared. So that's perhaps the easiest way. So that is 40,000, okay, and 4 km. 4 times this is 10,000, so it's 4k. So 10,000 times 25 is therefore 250,000. So therefore, the damping constant squared is less than this value, this 4 km. So as we saw about that criteria, that means that B is too small and the system is underdamped. So thus this is underdamped, the underdamped case. So that means that the general solution in this case is C e to the minus pt cosine omega prime t plus phi. Good. Okay, so let's find these terms. So P is equal to B over 2m. Okay, so what is that? That's 200 divided by 50. 2m is 50. 200, that's 4. Let's just leave it as 4. Okay. We'll of course remember that minimum amount of significant figures we have here is 2. Okay. All right. What next? Omega prime, and that is square root of omega squared minus b squared. And what is omega squared? So the natural frequency, or the frequency in the case of that there is no damping, that is k over m. That is, this over that is just 100, so this is 100. And here I've worked that out, that's 16, so square root of 84. And this will leave like this, because we can't reduce this to something else. Well, we could take out a 4, so this is 4 times 21, yeah, and then that means it's 2 times square root of 21. But that's not really simpler. Well, it's the same. It's more to write, so we prefer to write less. So let's just leave it like that. Okay. Good. Okay. So that means the general or the complementary solution is therefore xc. We give it the subscript c. So in other words, the general solution of this thing is therefore c e to the minus 4t cosine square root of 84 t plus phi. Great. Okay, so I found my complementary solution. And now something that is a somewhat common mistake is to forget that you're not done and now start to put in these initial conditions. Okay, so these initial conditions are for the entire thing, for our system, for our setup. And that is not a homogeneous case. Now we're still busy working towards that, so don't fall into that trap. Now this is this comes from being absent-minded. So we're not done. We've only done half of it. Now we've got to find one solution of this thing, just one. Doesn't matter which one, just one. And we figure out a way to do that. We call it the particular solution. And we've already seen that that particular solution, let's call it xp right off the bat, is equal to a, or I can find one in the form a cosine omega ft minus theta for the right choice of a and theta. And I saw that I can write this as a equal to square root of f0 over b omega f. Okay, that must be squared plus k minus m omega f squared and all things squared. Okay. Okay, now we just have to calculate this. And this I'm not even going to try to do without the calculator. Okay, so what do we... Okay, you can... Alright. Okay, so now, needless to say, here it's very easy to make a mistake, so just be careful. What next? Divided by square root of, okay, b 200. So no. Okay, wait a minute. The way this works, there should be a square there. Okay, wait. Now that I'm looking at it, oh no, wait. Okay, no, wait. Let's just see. Let's just look up the formula again. Yes, no, I am correct. No, I'm correct. The square should be on the outside. Good. All right, that makes more sense. Okay. Because this is a radius value that you get by squaring the x and y coordinates, so it doesn't make sense that the square is on the inside unless it was simplified to be on the inside. Okay, okay, so this should be 200 times 8 plus a square root of, what is k? 2500 minus, no, 2500 minus 25 times, is it 20? Yeah, it is 25 minus, multiplied by 64, 8 squared, and then the square of this whole story. Ooh, okay, 6.8, let's write it as 6.81. Okay, good. That should be okay. All right, now we need to find tan of theta. And we just have to be wary of tan inverse giving us a negative value, which if tan inverse gives us a negative value, then I just have to add pi as discussed. Okay, so this is b omega f divided by m divided by, what's that term? Oh yes, omega squared minus omega f squared. Okay, so in theta. Okay, so let's write. Okay, so that is okay, so I'm going to work out tan inverse of 200 times 8 divided by okay, but that's just 64. No, 25 goes 8 times into 200, so this is just 64 divided by, okay, let's see what we have here. Omega squared, we already saw that's 100 minus 64. Yeah, 8 squared 64. 100 minus 64, so that is 36. Okay. So theta is 1.06 plus n times pi. Okay, so we're going to take theta equal to 1.06, therefore. So we're going to take theta equal to 1.06, the smallest one that works. If this was minus, then I would have added 1 pi. Okay, so that's the particular solution. Let's give it a nice squiggly line. This pen is messy. Okay, xp is equal to therefore 6.81 times cosine of, where are we? Omega f is, oh yes, 8.0, well, let's write like that, 8.0 t minus 1.06. All right, okay, so thus the general solution of 1 is therefore the sum of these two. X equal to xc plus xp equal to, okay, c e to the minus 4t cosine square root 84t plus phi plus 6.81, sure, cosine 8.0 t minus 1.06, sure, okay, big thing. All right, so there's a general solution. So that differential equation, any and all solutions of it can be found in here for the correct value for c and phi. All right, so are we done? We're not done, even though we've written the entire page. We now actually have to still solve it. We need to find out c and phi. So for that, we have to use the initial conditions. So let's write the initial conditions is, okay, let's start. Which one will we use first? All right, well, let's start with that one. Okay, so now, well, okay, I don't know if I want to rewrite the function. Okay, I'm just going to submit the value so you can write down the function. All right, so x of 0 is equal to, let's see, what do we have here? Yeah. Fine. Okay, no, just remember what it was. Okay, I'll look at it from the side. So it is going to be c cosine phi plus 6.81 times cosine of minus 1.6106, so cosine of 1.06. Okay, hello, whoever that was. All right, and that is equal to minus 5. Minus 5.0. Great. Okay, so we can simplify this. So let's write that down. Okay, so we have to calculate some values here. So c cosine phi is therefore equal to, okay, minus 5 minus 6.81 times cosine of 1.06, and always of course check that you're on radians, don't forget. Minus 8.33, okay, minus 8.33. Okay, good enough. All right, okay, that's the first one. Okay, now how about the next one? Okay, so the derivative, okay, so now, oh, okay, yeah, I forgot about all this. Forgot how much work these problems are. Okay, so the derivative, I need to calculate now the derivative of this tremendous thing. Okay, but anyway, that's why I did calculus in first year. So minus 4. Okay, minus 4 c e to the minus 4t cosine square root 84t plus phi, and then minus square root of 84 c e to the minus 4t sine of square root of 84t plus phi. Okay, that does the one. Okay, the other one will be easier. Okay, and that one will just be minus 6.81 times 8. I don't know how much fun is it to calculate that by hand. So 6 times 8 is 48. No. So 6.81 times 8. So that is 48 plus 6.4 plus 0.08. Okay, so in other words, that is 54.48. Alright, so let's say 6.81 times 8. Okay, good. So let's leave that as 54.5 minus 54.5 sine of 8.0t minus 1.06. Okay, good. So you see how many places there are to make mistakes with these problems. So you have to definitely keep your head. Okay, so in this derivative, thank goodness, at least works out to 0. Well, not that that would have helps in any case. Never mind. Okay, so right. So let's see what do we have here. So this is minus 4c cosine phi. That is minus square root 84c sine phi. What do we have here? Minus 54.5. Okay, sine of minus 0.106, so that will be minus sine, so that will be plus sine of 1.06, and this should be equal to 0. Good. All right. So, and this is a point where some people get confused. How do I get past this point? I want c and I want sine phi. So where are the things that I want? There's c, the cosine phi, there. Okay, so I'm going to isolate cosine or c or something here. Well, I don't know. I don't see any other way. Let's see. There's the easy way, but I'm just trying to see if there's a harder way as well. Well, if you take out c common factor and you've got cosine, nah. Yeah, no, not really, not anything that not make you pull your hairs out. Okay, so anyway, so the simplest way to go forward here is to notice you've already know what c cosine phi is. You see that? You already calculated. So that term you can replace with minus 8.33. So then that term becomes something you can calculate. That one is something you can calculate. So you're only left with c sine phi. So you have to think a little bit ahead of these problems, make a concocted plan. So the plan is, oh wait, I can replace that with minus 8.33. So I can write this as c sine phi equal to something. And then I've got c cosine phi equal to something. But then I can divide the two and get what is tan of that angle, because the c's will cancel. All right, so good, we've got a plan. All right, so think a little bit ahead and make a plan. Okay, so we can write this as 4 times, okay, let's write it all at this on the right side. So let's save some space. Okay, I'm just going to save space and skip a step. So I'm going to write that on the other side, and then so square root 84c sine phi is equal to, therefore, okay, now this is minus 4 times minus, so this will be 4 times 8.33, 4 times a third, 1.33, okay. Okay, what, I lost track now. Okay, so plus 54 sine 1.06. Good. All right, so let's calculate this. This one is possible to calculate by hand, but that one isn't. So in any case, I have to do it, all of it, with the calculator. Plus 54 times sine of 1.06 4 times 8.33 plus 54 times 7 of 1. Okay, good. Right. All right, so where am I? I'm at... okay, so that value I will then divide by square root of 84. Okay, so I'm going to get that C sine phi is equal to 8.78. Okay, good. So therefore, I can now take, well, which numbers have we not used? 1 and 2. Okay, so let's call that 2 and 3, just to explain carefully what we're doing, so anyone else can follow the steps nice and easily. So I'm going to say 3 divided by 2, and then I'm going to get tan of phi equal to 8.78, well, minus 8.78 over 8.33. Okay, so negative value. So let's see what that calculates as. So phi is tan inverse of minus 8.78 divided by 8.33. So phi is equal to minus 0.8. Well, let's say 81. Okay, we're going to drop the last significant figures anyway, just tagging an x along for purposes of the calculations. Plus n pi, where n is any integer. Good. Okay, so now I can put this into either of these, so I can put it into 2 or 3 and calculate for c. And we'll preferably want a positive value for c. It's less of an imperative or in these kind of problems, but let's see if we can get a positive value. So let's use 2, so let's try phi equal to minus 0.812 into, and then that means that c is equal to minus 8.33 divided by cosine of this 0.812 minus cosine of x is equal to cosine minus x. Okay, are we okay with this? Is this correct? Cosine c, yes, okay. Oh, wait. Oh, I get a negative value. Okay, well, okay, so let's try. Okay, well, I mean, it's less of a concern of these kind of problems, but we like to keep those constants positive, so then c works out as a negative value. So I'm just going to, I shouldn't have deleted this. Okay. Okay, well, anyway, so if I try the next one, phi equal to minus 0.812 plus pi, which is equal to, well, let's just write down what that is, minus 0.812 plus pi. It's 2.33. If I try that in 2, then I'm going to get c equal to, and see now this one, I shouldn't have deleted that because it would have worked out to the same thing. What I did was minus 8.33 divided by cosine of, what did I say? Minus 0.812. That's what I calculated. But if I replace that with just plus the pi value, the only effect what it's going to be is it's just going to change the value of this cosine. That's all it's going to change. So I can already tell that in this case where I just use pi, the angle is with extra pi added, then the answer will just be positive version of that, so 12.1. Okay, good. So there I have it. So this, I've got a phi, I've got a c, and the c value, so I can write down the final solution. So x of t is equal to, all right, so where is that whole thing? Okay, so it is 12.1 e to the minus 4t cosine square root of 84t, and phi we calculated now as plus 2.33, and then the other rest we add already. 6.81 cosine 8.0t minus 1.06, and sure, and there is the fruits of our labor. And there, now you can answer additional questions if needed with this function. Okay, good. So all these kind of questions will follow the same format because the particular solution will work out the same way each time. This part, of course, can change because it could turn out to be critically damped or overdamped. So then this part will be a bit different. And in this case, underdamped is less ideal because it makes this differentiation part much longer, perhaps, than it needs to be. So overdamped would perhaps be the nicest one to have here. Good. But anyway, so there's the solution. Right, and to conclude, let's look at what that complicated function x of t that we calculated in exercise 1, what it looks like. Specifically, what it looks like compared to the transient and the steady state parts that we both calculated. And there we see it. The red part is what we actually see, the solid line, and that just merged with a dashed green line for the steady state. Okay, so the transient part with the dotted line, that simply dies out. It only has an effect on the final solution clearly for, it appears to be about the first second or so. Then the solid red and the dashed green lines are indistinguishable. So this gives a very nice visual justification of the terminology used, transient and steady state. So how long of a period the transient state will have an impact on the final solution? That will depend on the constants, such as specifically the damping constant. For a very large damping constant, you'll see a much longer time frame in which the transient part will affect the final solution. But here it appears as if after about 1 second it doesn't have an effect anymore. And you see that the long-term behavior, in this case long-term just being 1 second, what we see is indistinguishable from the steady state solution. So depending on questions will be asked, if asked how long it takes for something to happen, then it is for a particular problem, then it is normal to just simply answer the question in terms of the steady state expression directly and not even bother with the full final part, which contains a transient part, because that transient part just dies out very quickly. Now, of course, if a question is asking about something that happens very shortly after everything gets set into motion, then you definitely have to consider the transient part. But if it asks for something after a minute or so, then it's a good bet to simply use the steady state and only to answer the question. Okay, but anyway, this is for displacement. You may ask what it looks like for velocity and acceleration, and it's the same kind of deal. The final part, the final solution, just its derivative joins that of the steady state part, or the second derivative, that of the second derivative of the steady state. So it just shows that the same thing happens, which is obvious in the velocity and acceleration case as well. Okay, and that is it for the first lecture on forced harmonic motion.